Okay, so we talked about plane surfaces. Now we're going to talk about curved surfaces, as I promised. Here's just a cool picture from Toronto's Ripley Aquarium, where you can see where designing these tunnels, you would really want to take care in calculating correctly the forces acting on these curved panes of glass to ensure that they're strong enough and they'll withstand those forces. Here's also the Hoover Dam. A lot of times dams, especially for larger spans or much larger dams than just maybe a small river dam, are taking advantage of some of the mechanical advantages of using a curved structure. Especially when you're building with concrete, you want to make sure that the entire structure is under compression and it's not causing any sort of bending where you would have the inside edge maybe under tension like you would with a flat surface. So if you have a curved surface, the whole structure can be under compression, and concrete is very, very strong in compression. So it's not uncommon to see dams and other structures using curved surfaces to withstand the loads that fluids might exert on them. So just like we talked about before, I guess I'll redraw this for completeness, but we had, before we drew flat surfaces, now let's draw, doesn't have to be open upwards. Let's say our surface looked like this. This is the ground. This is our water. Here's our pressure profile. And the pressure that's acting on the surface is going to be always perpendicular to that surface. So here's an example of one where we have basically an overhanging dam, and then just like we did before, here we have some mound, and the force is acting on this surface. Maybe I'm exaggerating a bit. Could look something like this. So if we were to use the same approach as before, there's a few extra things we need to do. And because now that angle could be changing as we go further down into the fluid, we get deeper in terms of our h dimension, it'll be a little more difficult to actually derive the equations the same way we did before. And actually, I don't really know why we even teach the other way or do problems the other way, because if you use the same approach for curved surfaces, it kind of makes solving plane surfaces even easier. So basically now, because we have a curved surface, we want to find the same things, but we're going to look for them in a little bit different way. So our objectives now, if we go back up here, we want to find that reaction force. So let's say that reaction force is going to be somewhere here. And then for this one, maybe it's somewhere here. And it's going to have some line of action. Draw in black. So we're basically looking for that equivalent force, the resultant force, and the line of action. So we want to find resultant force F and line of action. Okay, a lot of material on that slide. So let's say we have this curved surface, and what we see here is basically the projection onto the vertical plane, and we could also draw the same thing of the projection onto the horizontal plane. Let's say it looks something like this. And at the same point as the center of pressure, maybe it's over here. So this would be our center of pressure for the vertical component of force. And over here on the right would be the center of pressure of the horizontal component of force. Horizontal and vertical. And our resultant force is going to be basically the vector sum of this horizontal and vertical component. So we're going to separate this now into horizontal and vertical components instead of just solving for the force, because that angle that force is acting on is not the same. So we're just going to do our analysis on the projections on the vertical and the horizontal directions. So our total reaction force, the total resultant force, is going to be the vector sum the horizontal and vertical components that we calculate. And that's going to be acting at some angle theta. And the last thing we need to know is where is that acting, and we calculate that location as our center of pressure. So the x of our center of pressure and the z of our center of pressure. So we essentially have four things we need to solve for. We need to solve for F, we need to solve for theta, we need to solve for our x center of pressure and our z center of pressure. So we need F, theta, z center of pressure, and x center of pressure. So the z center of pressure and x center of pressure in this case is the same as our x bar and y bars and with a plane surface, except the difference is now they're with respect to the bottom of that shape, the bottom of that surface. They're not with respect to the centroid of that shape. Because the shape is a curved surface, we're not going to do an analysis that looks at the centroid of the shape per se. We're going to do an analysis that looks at the centroid or the position of the projections of that shape. So the next thing we could write for resultant force said it's the vector sum, so the magnitude of that force is going to be square root of the sum of the squares of the components. So FH is the horizontal component and FV is the vertical component of our resultant force. And then our line of action has an angle of theta, which is equal to the inverse tan of our vertical component divided by our horizontal component. And its location, so the point that line of action passes through is going to be at XCP X center pressure, Z center pressure. So really we just need to find, I say four things, and I circled F and theta. We really actually need to find FH, FV, XCP, and ZCP. So these are the things we're actually going to be looking for. Once we have those, we can solve for everything else. Right. All right, so let's find our vertical component of our force first. So FV is the vertical component of a resultant force, and we can solve for this by solving the equation of equilibrium for adding up all the forces in the x direction. So if we think of it this way, the surface that is facing upwards, or the surface above the surface that we're doing analysis on, the reaction force of that surface must be supporting the weight of the entire fluid column above it. So that includes the weight of the air, the weight of the rectangular column that's above the surface, and then the weight of the water that's sort of contained within that surface, but directly above it. So if we do a sum of the forces in the z direction and say they're equal to 0, this would be equal to Fv minus the weight of the air minus W1 minus W2. So in this case, W1 would just be equal to the specific weight of the liquid times the volume, do big V for volume, and that's the volume of section BCDE. Is someone's mic on? I'm just getting some feedback here and there. Just double check if your mic is on. So yeah, the weight of section 1 is just specific weight times the volume of the section 1. We can just say gamma V1. The weight of section 2 is equal to gamma times the volume of section A, B, C. Or we'll just call it gamma times volume 2. And then the weight of the air, we can just consider that as a horizontal surface. And we know the pressure of that horizontal surface, and that's equal to the pressure of the atmosphere, or the pressure at that surface times the area of that surface. So the pressure of the atmosphere times the area of the section DE. So if both sides open to the atmosphere, and what I mean is if this on the other side is continued over and PA exists over here somewhere, then we don't have to consider the atmospheric component, because that same pressure from the atmosphere is going to be pushing up from the bottom. So all we'd be left with would be just weight 1 and weight 2. So if both sides open to atmosphere, then we can just say PA is equal to 0. Let's ignore PA, and we get our FB is equal to weight 1 plus weight 2. So we found FB. So now let's find, using the same method as before, where is the center of pressure for the vertical component of our reaction force. So the X center of pressure is going to tell us where, from the left-hand side of that shape, as drawn here, that vertical component of force is going to be acting. So just like we did from before, we're essentially, in order to determine where this center of pressure is acting, the line of action, the vertical component, or I guess the horizontal component, XCP, we're going to just balance the moments from some point. So we can choose arbitrarily, our origin is going to be here, and we'll say this direction is where XCP is acting. This is our x-axis, and then this would be our z-axis. So we need to figure out what is the distance XCP that's going to balance out the moments from all of these other forces. So this is going to be the distance of x2, this is the distance x1 for that moment arm, and then we have x air. So we need to balance the moments about O. So if we do that, sum of the moments about O is equal to 0. Let's choose clockwise to be positive. So we end up with W1 times X1 plus W2, X2 plus W air, X air minus FV times XCP is equal to 0. So if we rearrange this, we just want to solve for XCP. We know FV already, we just calculated it. So we have XCP is equal to W1 X1 plus W2 X2 plus W air X air divided by FV. So we'll just highlight this. This is our equation that we'll use to solve for the center pressure in the X direction. So that was simple, relatively. So now let's look at the horizontal component of our force. The horizontal component of our force, if we were to draw this again, we would draw our pressure profile. Extend our pink water over here. So our pressure profile due to the liquid is 0 at the surface. It increases linearly as we go down in depth, and we only care about this section here. And so if we think back to how we solve this with plane surfaces, we can go through the same steps, except now we have to integrate over a curved surface. But if we just look at the projection, well, all we care about right now is finding the equivalent force. We don't really care too much exactly where it is right now. So if we just think of this as a distributed load, we can calculate where that distributed load is relative, or the total amount of the distributed load, using the pressure at the center of gravity of the horizontal projected shape. So our center of gravity for the projection, if we have a regular shape, it's going to be somewhere near the middle. So that's our center of gravity. And we can calculate the area of section AC. So this has some area of that shape. Remember the horizontal projection of that shape. So we can just write FH is actually equal to the integral from A to C, the pressure dA, which is exactly how we would have started for the plane surface. And we would find that it's just going to be equal to the pressure, the center of gravity, times the area of that horizontal projection. So area of horizontal projection. If we think back to our plane surfaces, we had that sine theta angle. Well, the area of the actual shape, a plane surface times sine theta, is the area of that projected surface. So now, because that surface is curved, instead of calculating that sine theta and integrating over everywhere, we can just look at that projection. And if we know the area of the projection surface for a regular shape, then it can be much easier to solve. So for example, if we had a hemispherical dome, and we knew the radius of that hemispherical dome, it was underwater, the horizontal projection of a hemispherical dome would just be a circle. And we know the area of a circle, we can calculate that, we know the radius, so on. So just some definitions here. PCG is the pressure at the centroid or center of gravity of the horizontal or the horizontal projection or the vertical plane. So of the horizontal projection of the area. So we'll call this on the Z axis. I'm not sure how to draw this. Maybe I don't want to make it too confusing, but let's say that area. No, I won't add it. Think back to the diagram we had up above, where we have our horizontal projection. So this is the, I'll draw on a page that, oh, iPad didn't like that. Horizontal compression or horizontal component, horizontal projection. So that's all we mean. The area that you would see if you were to view this from the side. And that horizontal projection area is area AC. So that's the horizontal component of our force, our resultant force. Now we want to find the location of the Z center of pressure. So let's draw some things here. We know that in this shape, our center of gravity will be some location. And our center of pressure is going to be where that force is acting. So this is going to be our ZCP. Extend this out. This distance here is going to be our Z for our center of gravity. So the distance from the bottom of our shape to our center of gravity. And then same as before, this distance here downwards is going to be our Y bar. So that is the distance from our center of gravity to our center of pressure of that horizontal projection of the area. So we know Y bar from before is equal to negative gamma, negative specific weight times Ixx times pressure times center of gravity times area of AC. This had a sine theta in it before, but if we're looking just at the vertical plane or the horizontal projection, then that sine theta is 90 degrees. So sine theta is just 1. So we can get rid of that. So all we're left with, we rewrite it in the form that we had it before, Ixx divided by height at the center of gravity times the area. We'll call this AH, areas of the horizontal projection. So in this case, again, we'll write Ixx corresponds to the vertical plane of surface AC. it's confusing calling it vertical plane or horizontal projection. Hopefully it's not too confusing. If you just think of, when we're talking about horizontal components, we're just looking at the view from the side. When we're talking about vertical components, think of we're looking downwards at that shape and how that appears when we view it from the side or from above. So finally, we know y bar, we know ixx for the shape if we know information about the shape. So we can calculate the z distance from the bottom of our shape to our center of pressure is equal to the distance to our center of gravity plus y bar. We know y bar is going to be negative, so that z center of pressure is going to be below our z center of gravity. So remember, y bar is always less than or equal to 0. So that's curved surfaces. So let's do some examples and see. We have actually a pretty good chunk of time. We should be able to get through these examples. I think I have 2 or 3 of them. Okay, example 1. The floodgate shown represented by surface AB is a circular arc with a radius of 2 meters and a width of 1 meter. The fluid above surface AB is water and is open to the atmosphere. The back side of the floodgate is also open to the free atmosphere. Determine the magnitude and line of action of the resultant hydrostatic force the water exerts on the floodgate, and assume a specific weight of water is 9,810 newtons per meters cubed. So what do we have to do? We have to find the magnitude of the hydrostatic force, F. And that's going to be equal to the square root of the sum of the squares of the horizontal and vertical components squared. And then we have to find B, second part, the line of action. So the line of action what we mean by when we say line of action is we want to find theta, the angle of that line of action, and then the point x at the center pressure and z at the center pressure at that point acts through. So let's begin. Let's go through our steps from before. Let's start by finding our vertical component of our force. So the vertical component of our force is going to be this component pointing upwards. And we use the sum of, we need to balance the forces in the y direction or the z direction. Let's draw our coordinates x and z. So we do sum of the forces in the z direction are equal to 0. So we have v pointing upwards, and then on the other side of the equal side we'll have weight 1 and weight 2. Now it's said that both sides of this is open to the atmosphere, so we could ignore pressure due to the atmosphere. So what is weight 1? Weight 1 is going to be gamma of water times volume of B, C, D, E. So what is the volume of B, C, D, E? So we know this is, if we read the question again, this is a circular arc with a radius of 2 meters and a width of 1 meter. So if we were to look down from the top, this would look like a rectangle. So top view, we would have 1 meter by 2 meters. right? And I'm going to try and add some, this might be kind of what it looks like. I tried to add some horribly drawn three-dimensional shading. So that volume would just be 2 square meters. So we know gamma is 9810, right? 9810 Newton per meter cubed times 2 square meters. Sorry, 2 times the height, which is 4. That's meters cubed. So we should end up with a force, which is good. We get weight 1 is equal to 78,500 newtons. So for weight 2, gamma of the water times the volume, and this time our volume is going to be ABC, or the volume of that quarter pipe section. So what is the volume of that quarter pipe section? It's going to be 1/4 of the volume of a cylinder with a radius of 2 meters. If we imagine this whole shape is a cylinder, we're going 1 meter into the page, we're going to find the area of that cylinder and we're going to divide it by 4. The area of a cylinder is pi r squared times the width into the page. We're going to take 1/4 of that. So it's going to be gamma times W times 1/4 of pi. Our radius is 2 meters squared. Let's write this as r for now. R squared times our width into the page. So 9810 newtons per meter cubed times 1/4 times pi times 2 meters squared times 1 meter into the page. And this should give us 30,800 newtons. So FB is going to be the sum of those two forces, and FV we'll find as 109.3 kilonewtons. We'll just write it in kilonewtons. So now what about the horizontal direction? In the horizontal direction, FH, we said that FH is equal to pressure at the center of gravity times the area of the horizontal projection, or the area of section AC. So where is the center of gravity of that horizontal projection AC? So if we were to look at this from the side, the horizontal axis, it would just look like a rectangle, and a rectangle is symmetric shape. Its center of gravity, or centroid, is right in the middle. So we can draw the centroid right here, and we know that the distance from the surface to that centroid is going to be 4 meters plus half of the distance here, because it's a semicircle that's 2 meters. So this distance here is going to be 4 plus half of 2, which is 1, so it's going to be 5 meters. And the area of that rectangle, if we were to view it from the side, it would be 1 meter wide and 2 meters tall. So the area is 2 meters squared. So our horizontal force would be our pressure at a depth of HCG times the area of H. So we have 9810 newtons per meter cubed times our height, which is 5 meters to the center of gravity, times our area, which is 2 meters squared. And if we do this, we get a horizontal component of force is equal to 98.1 kilonewtons. Okay, so we found two things. Now we can find our theta if we wanted to. So theta is equal to tan inverse of FH over FV, which equals to tan inverse of, what was our FH? 109.3 divided by 98.1. And this would give us 48 degrees. So that 48-degree angle is this angle here. So an angle from the horizontal. So we have theta. We have our resultant force, F, is equal to 109.3 squared plus 80 or 98.1 squared. And our resultant force is equal to 146.9 kilonewtons. Oh, yes. Thanks for pointing that out. Yeah, it's FV or FH. I think that's what I wrote earlier, right? Right. So we have the angle of our line of action. We have our total resultant force and the components. Now all we need to do is solve for where are those components acting. So XCP and the Z direction of our center of pressure. So we said that XCP is equal to weight 1 times X1 plus weight 2 times X2, all divided by vertical force. So weight 1, if it's a perfect rectangle, means X1 is going to equal 1. So that one's pretty straightforward. What about weight 2? What is X2? Well, if you use the properties of the centroid of a quarter sphere, so for one quarter circle, the centroid of that shape, X2 is equal to 4 times the radius divided by 3 times pi, which is equal to 0.84 9 meters. So we know all those values. We could then say XCP is equal to weight 1, which is 78. We calculated above. 78.5 kilonewtons times 1 meter plus 30.8 kilonewtons times 0.849 meters, all divided by 109.3 kilonewtons, and we should get X center of pressure location is equal to 0.957 meters. So one more, we need to find the Z center of pressure. So the Z center of pressure is equal to Z center of gravity plus Y bar. So Z center of gravity is just, we could also just say H center of gravity plus Y bar was IXX divided by H center of gravity times area of the horizontal projection. So it seems in this case, if we want to do it this way, it doesn't matter really where we choose as our reference. We could choose from the bottom or from the top. So let's keep it consistent what we're doing. Instead of using H here, I'll use Z center of gravity still. So that's with reference to the bottom. So Z center of gravity of that area we said was 5 meters from the top, so that'd be 1 meter from the bottom. So 1 meter plus this equation for Y bar should have a negative there. So minus IXX, which we calculated above, did we not? No, we didn't. So IXX for that rectangle shape, when we look at that side view, is it's a rectangle, so it's width times length divided by, or length cubed divided by 12. So we have a width 1 into the page, a length of 2 meters tall, to the power of 3, and that's all divided by 12. And then this is going to be divided by the height h to the center of gravity, so that's 5 meters in depth, and times the area, which is 2 meters squared. So if we do this, we should get 0.933 meters. The Z center of gravity, how we've drawn it, and how we've done all our referencing, the Z coordinate is going from the bottom upwards. So the Z distance from the bottom to the center of gravity plus the distance from the top to the center of gravity, which is HCG, should add up to the total depth. So yeah, ZCG plus HCG should add up to 6 meters, which I think is what we have. So ZCG I have is 1 meter. We have HCG is 5 meters, so that's total 6 meters. You could do this the other way, and you could just say references from the surface. And if you wanted to, you could say Z center of pressure with reference from the top is equal to H center of gravity plus that y bar, which is going to be negative, or plus the absolute value of that y bar. And that would give you the same answer, except it would be with reference from the top. So you could say, or 5.067 meters from surface. So that's the point that resultant force is acting. So if we were to now try to solve, like our other problems, our questions of what are the reaction forces of the supports, maybe at A and B, we would be using these distances, XCP and ZCP, for calculating those moments of where that force is acting. It may not necessarily, for doing this analysis, be acting actually on the surface. But the equivalent moment is acting at the distance XCP and ZCP from that location that we referenced, which is down here. Oh, the bottom corner, right at A. So it really helps when you're solving these problems to make sure that you keep your diagrams clear and can draw where everything is. You can choose references wherever you want. Just make sure it's consistent all the way through your problem and you're not changing it partway through, because that's when you can introduce errors and make mistakes. So if we wanted to finish this drawing off, we would maybe just draw our shape at the bottom, and we would have our resultant force, theta, XCP, and ZCP. Draw it this way. So that's where everything would be. And like I just said, it doesn't actually have to be acting right at that point. Actually, this force is drawn. This would be the force the fluid exerts on the barrier. So the force we actually solved for is the force of the barrier acting on the fluid. So I should draw that arrow the other direction. So that's what our problem looks like. That's what we just solved for. So we got just about 10 minutes left. This question is not as long. It's kind of a bit of a concept question. But we'll try and go through it in 10 minutes. And then if there's questions at the end, if people have questions, we can try to answer some questions. So in this case, we have a hemispherical surface that protrudes out into, let's say, some tank. Maybe it's a dome in an aquarium that we're looking through. And it's asking to find the X, Y, and Z components of the resultant hydrostatic force acting on the hemispherical surface. Water is enclosed in a chamber and its surface pressure is 35 kPa. So it's telling us that the pressure at that surface of that chamber is completely enclosed. So it's not atmospheric pressure, and it's 35 kPa. So in this case, we're looking for the absolute pressure, not the gauge pressure. And the hint is that it tells us it's in an enclosed chamber. So let's start by looking at the horizontal direction. So if we have a horizontal component, we know, let's just draw again. We care about this pressure profile, just where that actual shape is. It's a hemisphere with a radius of 0.9 meters. So we can write Fx is equal to pressure at our center of gravity times the area of the horizontal projection. And that's equal to gamma times the height, or depth rather, h of the center of gravity, plus PA times the area of the horizontal projection. So the area of the horizontal projection is just going to be the area of a circle with a radius of 0.9. So it's pi r squared, which is pi times 0.9 squared. Let's include that in our calculation. And the height to the center of that hemisphere is actually going to be also the center or center of gravity of that sphere projection. So we can write it with all those terms. Hope no one gets motion sickness. So we add up all those terms. We have our gamma for water is 9.81 kilonewtons per meter cubed, times our height is 3 meters shown on the diagram, plus our pressure at the atmosphere, or at the opening in the PA, which is 35 kPa. And then this whole thing is going to be multiplied by pi times 0.9 squared. And that's meters squared. So our final answer, if we do this correct, should be 163.9 kilonewtons. So that is the X component of that force that's acting on that hemispherical dome. So conceptually, if we think about the, let's say, the y direction, as the direction show, the y direction would be on, like, through the plane of the page, or through the page. So what do you think the reaction force in the y direction would be for this hemispherical dome? So what would be Fy? Look back at this top figure. So if we think of, I've got some answers saying 0 and some saying the same as Fx. So if we think about it, if we look at the left half, so if we were to, bear with me, pretend this is an eyeball, and we're looking at it, we have pretty eyelashes. So if we're viewing this from the side, we're going to see two halves on the left and right. And there's going to be a force of the left side fluid pushing towards the right, and a force of the right side fluid pushing to the left. So we only care about the forces that are acting in that y direction. And because it's protruding both sides, and the pressure at the same height is the same, the pressure acting on both sides is going to cancel out or balance out. So in the y direction, the resultant force is actually 0. There is no equivalent force. Think about submerging anything underwater. If we submerge it, there's no difference in pressure between the left and the right. When we hold a pool noodle underwater, it doesn't just, well, it might, but it doesn't shoot to the left or right or something like that just because of forces underwater. It just wants to come back up due to its buoyancy. So because it's symmetric, Fy is equal to 0. And that's because of symmetry. So we've got Fy. Last part is Fz. So how can we solve for the force of the vertical component? So if we do a force balance on a diagram of that hemisphere, we have the force of the upper fluid, and it's counteracting the force of the lower fluid. But what is the upper fluid force and what is the lower fluid force? So let's think of it this way. Hypothetically, if this hemisphere was filled with water, its weight would be borne by the surrounding water, taken care of by the surrounding water. So the vertical force of the surrounding water is equal to the weight of the hemisphere when it's filled. So because the hemisphere is completely submerged, the vertical force surrounding the water is equal to the weight of the hemisphere if it was filled with that fluid. The vertical force is equal to the weight of the hemisphere if it was filled. So what I mean by this is if we had that hemisphere completely filled with water, the resultant upper and lower forces would be zero. There would be no forces acting on it. That fluid would just be in equilibrium. The weight of the fluid would counteract those forces. So taking out that fluid mass and weighing that must be the force that is exerted on that bubble when it's empty. And that is essentially Archimedes' principle. So we can say that the Z force is equal to the specific weight of water times the volume of the hemisphere. If it was filled with water, that's what it would weigh. So this is equal to half of a hemisphere. The volume of half of a hemisphere is 2/3 times pi times r cubed. So we can finally write that Fz is equal to 9.81 kilonewtons per meter cubed times 2/3 times pi times our radius, which is 0.9 meters cubed, which would give us 15.0 kilonewtons. And we'll see conveniently that in our next lecture, when we talk about buoyancy, this is a good rise into buoyancy. This is exactly what is called the buoyant force. So because we have the surface completely submerged, this would be the buoyant force acting on that submerged hemisphere. And we calculate it the exact same way. Good. Are there any questions about forces on surfaces? Are we comfortable with the stuff today, or is there anything that's confusing, or maybe we should just sit on it for a minute, try a few questions? If you can visualize what's happening in the projections of these surfaces in three-dimensional space, then these problems become quite a bit easier, especially if your diagrams are good. It can easily get confusing if you start off with the wrong diagram. So make sure when you're drawing your problems and you're showing your diagrams for your forces and different sections, you're taking care of everything. Go through these examples again on your own. Try and do them on your own without looking at the solutions and see if you can get the same answer. It would be good practice. So yeah, if there's no questions about today, then second quote of the day is from Galileo. And he said, wine is sunlight held together by water.